So good morning to everyone. In the previous lecture we discussed formulation of the governing differential equation, that is represented by A into d square y by dx square is equal to mx. Now let us see one simple problem: deflection of a cantilever with a point load at the free end by double integration method. As we know that we have so many techniques or methods to find the slope and deflection at any section. So in the first problem, the first method is double integration method. For that, let us consider a cantilever beam. So this is a beam. One of its end is fixed, that is at and A. The overall length of the beam is L. As per the given a point load W at the free end, so the free end is P, a point load of magnitude W at the free end. This is the one. So we know that A into d square y by dx square is equal to mx. Initially we have to find out the bending moment equation. Bending moment equation, say as equation mx, m suffix x. For that, let us consider a section xx. So, section xx. Section xx at a distance x from the free end. X from the free end. Here the x value increases from B to A. This is the direction of the x. It means the x value is 0 at B, the x value is at A. This is the configuration of the problem. Now let us formulate the bending moment equation. So whenever the cantilever beam is subjected to a point load at free end, it's deflected as shown in figure. It is deflected. So I think that it shows the hogging moment. It shows this is the deflected curve. Deflected curve. So it produces the hogging moment. So hogging moment is taken as negative. What about the definite perpendicular distance from the section XX to the line of action of the force W? This is the section XX. So this is the line of action of the force. Line of action of force. Line of action of force. Alright. So there is a definite perpendicular distance from the section XX to the line of action of the force is X. We know the magnitude of the force W, and we know the line of action of the force and definite perpendicular distance to the line of action of the force from the moment center, say as X is. So that is equal, the moment becomes W into X. This is the bending moment equation. So now, as per the governing equation, EI into d square y by dx square is equal to mx, say equation number 1. Substitute mx value in this equation, EI into d square y by dx square is equal to minus w into x, say equation number 2. For getting the slope, integrate the equation number 2 once. So let us see what about the slope. Let us calculate the slope. So to obtain the slope, just integrating the equation number 2 on either side. Therefore, integral ei into d square y by dx square is equal to integral minus wx. So, we know the equation. Then simply integrating it. So, what about that? We know that, therefore, ei into dy by dx is equal to minus w into x square by 2. Since x power integral x power n into dx is equal to x power n plus 1 by n plus 1 plus c1. Say this is equation number 3. So here we have to find out the c1 value. That is the constant of integration. So that is obtained by imposing the boundary conditions. So what about the boundary conditions? Boundary conditions. So let us see the geometry or the deflected curve. So this is the initial position of the curve. Say as this is the fixed end at A. So whenever the beam is subjected to a load, it is deflected. Whenever the beam is subjected to a load W, it is deflected. So this is the deflected curve. This is the deflected curve, as we know that. Now, what about the slope at B? This is the B. This is the deflection. Let us see YB. What about the slope? As we know that the direction of the X is taken. It means, so here origin taken at B. Here origin taken at B. It means the X value start with 0 at B. So, and it is at A, X value becomes L. So, I think that the slope, that is dy by dx, is 0 at A. It means, suppose, let us say this is the B. If you draw the tangent at B, this is the tangent, alright? So, this is called as a tangent, alright? So, what about the slope? What is meant by slope? Suppose if you measure the angle at point B horizontally with the tangent. So, this is the tangent at B. So, this is a horizontal line drawn at B. So, the angle between the tangent and horizontal line is called as slope. That may be represented theta B. Here theta B is equal to dy by, so dx at B. It means that is the slope. Again, suppose this is a point C at a distance, for example, L by 2 from the left hand. So, what about the slope at a particular point? So, simply this is a tangent drawn at point C. This is a horizontal line drawn at C. If you measure the angle between these two lines, that is as theta C. Of course, the slope must be in radians in calculation purpose. Now, similarly, draw the tangent at A, alright? This is the tangent at A. So, if you draw the horizontal line at A, those are coincide. It means there is no angle between the tangent and horizontal line. It means dy by dx value is 0 at A. Dy by dx value is 0 at A. It means at x is equal to L. So, dy by dx is equal to 0. The slope is 0, yet x is equal to L. Substitute x is equal to L and dy by dx is equal to 0 in equation number 3. Therefore, finally, that equation becomes EI into EI into, what about the EI into what about the dy by dx, that is 0. dy by dx is equal to 0 is equal to minus w into, what about the x value? X is equal to L by L, x is equal to L, that is equal to L square by 2, L square by 2. So, dy by dx, EI into dy by dx plus, what about the next value? That is C1. Therefore, C1 is equal to W L square by 2. Substitute C1 value in equation number 3. So, therefore, EI into dy by dx is equal to minus w by 2 into x square plus wl square by 2. Say equation number 4. This is called as equation for slope. This is equation for slope. So now you can find out the slope at x is equal to 0 and the slope at x is equal to a. So therefore, we know that EI into dy by dx is equal to minus wx square by 2 plus wl square by 2. So this is the equation for the slope, that is equal to EI into dy by dx is equal to minus wx square by 2 plus wl square by 2. So what we have to calculate? You have to calculate the slope at B. It means at x is equal to 0. So again, better to redraw that. This is the initial position. So what about the deflected curve? This is the deflected curve. This is and A. This is and B. This is the slow deflection. This is the, for example, B dash. Just I would like to find out the slope at a particular point B. So this is say as theta B. So therefore, at x is equal to 0. At x is equal to 0. Substitute in the above equation EI into dy by dx is equal to minus w into 0 square divided by 2 plus wl square by 2. So this term becomes 0. Therefore, dy by dx, here that may be represented theta b is equal to 1 by EI into WL square by 2. This is the slope at a particular point, that is B. Now let us see the slope at A. Now slope at A, it means at x is equal to L. It means substitute the x value which is equal to L in this equation. So therefore EI into dy by dx is equal minus w by 2 into L square plus WL square by 2. So what about the value right to the equation? This is WL square by 2 minus this is WL square. So it becomes 0. EI into dy by dx is equal to 0. It means the slope at A is 0. Therefore, theta A is equal to 0. So this is the procedure to calculate the slope. So now find out the deflection. So it means integrate this equation once again and impose the boundary conditions. For that, let us see what about the equation. Equation for slope EI into dy by dx is equal to minus wx square by 2 plus WL square by 2. Say equation number 5 for example. Suppose if it is integrate once again, we will get the deflection. So deflection. So this is the deflection is represented by y. So it means integrate the equation number 5. Integrate the equation number 5. Integrate the equation number 5. So integral EI into dy by dx is equal to integral minus wx square by 2 plus WL square by 2. So finally it becomes EI into y is equal to minus w by 2 into x cube by 3 plus WL square by 2 into x plus c2. Here we have to calculate the constant of integration c2 by imposing the boundary condition. What about the boundary condition? This is the boundary condition. What about the deflection at A? Let us see again. This is a cantilever beam as usually. This is the initial position. The new position. This is the deflected curve. As we know that this is and A, this is and B. This is the deflection at B, which is YB. I think that this is the deflection at A. Definitely deflection at A is 0. Deflection is 0 at A. It means at x is equal to L. At x is equal to L. So substitute the x is equal to L. So therefore slope. Sorry, that is not slope. Deflection. So deflection deflection y is equal to 0 at x is equal to L. Substitute y is equal to 0 and x is equal to L in equation number 6. Simply that becomes EI into 0 is equal to minus WL cube by 6 plus WL cube by 2 plus C2. So that is equal to, after integration, that is C2 is equal to, what is that value? So that is equal to, so this is 6 WL cube by 6 minus plus, simply that is better 2 is equal to 0 is equal to 0 WL cube by 6 plus 3 WL cube plus C2. This is becomes 0 is equal, so 2 WL cube by 6 plus C2. Therefore, C2 is equal to WL cube by 3. Substitute this value in equation number 6. So therefore, EI into y is equal to minus W x cube by 6 plus WL square by 2 into x plus WL cube by 3. So this is the equation for deflection. This is equation for deflection. This is the equation for deflection. What about the deflection at A? What about the deflection at B? Therefore, substitute at x is equal to 0 and x is equal to L. So finally, by substituting x is equal to 0 and x is equal to L, the deflection is 0 at A and deflection is maximum at x is equal to 0. The deflection is 0 at x is equal to L. By substituting the x is equal to 0 in this equation and x is equal to L in this equation, we find out the deflection at A and B. So this is the procedure to calculate formulate the slope and deflection equations. Now let us see one more typical problem. So a steel beam of circular section, cross section is very important one, with a diameter of 50, this is given, is used as cantilever. So this is the boundary condition, cantilever of length 3 meters. Length is 3 meters. How much load, that is W, how much load can be safely applied at the free end of the cantilever beam? If Young's modulus of a beam is 200 gigapascals and deflection is not to exceed, so deflection not to exceed 1 mm, slope is not to exceed 0.2 degrees. So let us see this is a cantilever beam. Alright, this is the cantilever beam of length 3 meters, of length L is equal to 3 meters. Subject to a load W is to be calculated. So as per the notation used so far, this is the direction of the x. Let us consider x at a distance X from the load W. This is the weight. This is the end A, this is the end B. As usually the beam is deflected. This is the maximum deflection at B, which is represented by YB. So initially we have to calculate as per the derivation EI into d square y by dx square is equal to mx. So we can formulate the mx value. What about the mx? So mx is equal as usually minus. So w into x, we know that. So initially calculate the moment of inertia I. I is equal to pi d power 4 by 64. Since it is a circular cross section, so this is the diametrical axis as represented by xx or yy. The moment of inertia of the circular section about its diametrical axis is pi d power 4 by 64, which is equal to pi into 50 power 4 divided by 64. Finally, that becomes 30.68 into 10 to the power 4 in mm power 4. It is converted into meters power 4, that is equal to 30. Again, the modulus of Young's modulus is equal to 200 gigapascals. So that is equal to 200 into 10 to the power 6 kilonewtons per meter square. Now let us see the deflection. So y is equal, here y is equal to y maximum, which is at the free end, as we know that. So this is y maximum. This is y maximum. So the length of that, we know that w is equal to w into, so 3 cube whole divided by 3 into E is also known, that is 200 into 10 to the power 6. I is already calculated, which is equal to, so 30.68 into 10 to the power minus 8, that is into, so 30 into 30.68 into 10 to the power minus 8. After conclusion, so we know the y maximum, which is equal to, so 1 into 10 to the power minus 3 is equal to w into 3 cube whole divided by 3 into 200 into, so 30.68 into 10 to the power minus 2. Finally, the w value is 6.818. Then, so we know the slope. What about the slope? That is given 0.2 degrees. In calculation, for the calculation purpose, that must be converted as radians. That is pi by 180. It is 49.0.49 into 10 to the power minus 3 radians. So, and we know the formula which is derived, that is w L square by 2 into EI. So, already w is calculated or I is given, that is equal to 0.49 into 10 to the power minus 3. So, w into 3 square whole divided by 2 into 200 into 10 to the power 6. So, into I is equal 30.68 into 10 to the power minus 8. Finally, the W value is 23.8 newtons. So, with considering the deflection, so the W value is 6.818. With considering the slope, the W value is 23.28. So, the preferable one is the 6.81 newtons is the safe load. So, excess amount of the load, the minimum load is the safe load. So, this is the way or the procedure to find out the slope and deflection. Today, we covered one numerical problem with the geometry, that is the deflection of a cantilever beam subjected to a point load W at a free end. So, initially we have to concentrate on the two parameters. One is, so formulation of the bending moment equation mx. Second one is the boundary conditions, the slope and the deflection or minimum, that is 0 at the fixed end. So based on that boundary conditions, we can find out the constant of integration C1 and C2 and substitute these values in both the equations. Finally, we formulated the slope and deflection equations. Then we solved one numerical problem. Tomorrow we will see the same cantilever beam subjected to a uniformly distributed load over entire span and linearly varying load over entire span. Thank you.